Okay. CAD CAM. You've all heard the phrase. All you've dealt with up to now is CAD, right? Either SolidWorks or that other one. I think you can tell which one I prefer. But anyway, I want to deal with CAM now, the second half of that phrase, computer-aided manufacturing. I want to get from your design through my CAM system to that machine and finished part. Okay, the CAM system we use is GibbsCAM. We started with it 20 years ago. We started with it because it had the lowest learning curve of all. I don't know if I can still say this because 20 years later, they've added so much more power to this. And with power comes confusion. But anyway, I'm going to help you step through it. And all I'm going to deal with basically is the same level that I did back then, because we found that that does 95% of what you guys do. Hopefully, we're going to get you back in here to actually make things. But as for now, I'm the best you get. All right, GibbsCAM. This is a regular CAD drawing, a solid model. Gibbs is going to machine solids, geometry, any combination of both. For simplicity, I'm going to deal with 2D geometry. And the first thing I'm going to look at is called a document window. It says I'm using a 3-axis vertical machining center. I'm machining plastics. And I come down here, and this is referred to, they call it stock size. I'm not really crazy about that. I'd rather call it the stock envelope. Because if I define this exactly as my blank size, and then I try to machine outside of that, Gibbs doesn't recognize it because I've told it there's no material out there. That's why I'd much rather refer to it as a stock envelope, okay? It's basically a 2x4 blank, but you've seen I've given a 200 thousandths extra all the way around. And I come over here to probably the most important number in this window. This is the rapid traverse clearance level in Z. And when I say rapid traverse, if you look at the side of that machine, it says 1,000 IPM. That stands for 1,000 inches per minute. It travels in rapid. At that speed, by the time you realize there's something in the way, you're already looking at a pile of rubble. You cannot react as fast as this machine goes, okay? This is the first place we're going to see this. We're going to revisit it all the way down the line. So I'm going to close that. The next thing I need is cutting tools. So I'm going to start with tile number 1, which corresponds to magazine position 1 in the machine, right down the line. Tile 2 is magazine 2, 3, 4, and so on, up to 20 in this machine. Tool number 1 is a 1/8 diameter end mill. For those of you who've never seen an end mill, this is a 1/2 inch diameter end mill. I'm not allowed to pass it around anymore. This is a 3-flute high-speed steel 1/2 inch end mill. I'm going to open up tile number 2. That's another end mill, only it's 1/4 inch, it's twice the diameter. This refers to the length of the cut, or the length of the cutting edge. Or in industry, they call it the flute length. Now, I don't know why they decided to define the material that isn't there, but they do, they call that a flute. So whatever flutes it is the same amount of cutting edges. And that has a bearing on the other thing that I didn't discuss in this. This is an actual material database. So I selected plastics, but it has a ton of materials in there. And based on your cutting tool material and the number of flutes, it's going to bring back suggested speeds and feeds. All right. Tool number 9 is a thread mill, and tool number 10 is a 1/4-20 tap. So now I'm going to use my CAM processes. I'll drag tool number 1 into CAM, and I get, okay, here's all of my options for machining processes with this tool. What we're going to deal with in this demo is these first four. They are the basic ones. The first one is holes, anything to do with hole making, spotting, drilling, reaming, tapping, broaching, boring, and I'll end at B. The next one is contours. That's going to drive a tool around a geometric boundary or a solid edge. The next one, I kind of disagree with GibbsCAM on this one. They call it roughing. To me, that really doesn't tell you what it does. I'd rather refer to it as pocketing, because it's going to machine away all the material within a boundary to a defined depth. To me, that's a pocket. All right? And the last one I'm going to talk about is threading. This last one is surfacing. Anytime we have a surface in this machine that is not either parallel or perpendicular to my work table, it's pretty much going to be a surface that requires some raster machining with a ball nose end mill that takes a huge program and a lot of time. So we try to avoid surfacing whenever possible. So my first operation, I said, is going to be holes. When I call up the holes, it gives me all of these cycle options to create a hole. The first one says feed in, wrap it out. That's a spot drilling command. Come over, drive to depth, and get out. The next one, feed in, feed out, is say for a reamer. We come over, we drive that in a feed rate to the bottom and feed rate back out again. The next one is a tapping cycle. That just matches a feed rate with an RPM to drive a tap in and out, assuming that you have somewhat of a flexible tap holder. The next one is rigid tap, and I'll talk about that when we actually do it. Peck full out. Has anybody used a drill press? You start the chips coming out there, then you back the drill all the way out to let the chips fall off. That's peck drilling. This one is peck drill full out. The next one they call peck drill chip breaker. You go down, and instead of withdrawing it all the way, you just pause, and that pause breaks the chip. Now, you can get away with that unless you're into a really deep hole. Okay. Rough mill bore, I've never used. The next one we will use, that's called finish mill bore. And I'm going to select that. Now, here's my clearance levels again. I said we're going to revisit this all the way. Top of my workpiece is 0.25. And for the bottom, I'm going to go to minus 15. I want to make sure that this tool goes all the way through and cuts it out instead of at Z0, which is actually the bottom of the workpiece. Okay? When I go to here, my material database brings back a speed and a feed. Now, this one's pretty reasonable. This database is geared towards the production industry, where, you know, an extra 5 seconds on a cycle is the end of the world to those guys. All right? In a prototype environment that we're in, I'd like to calm these down a little bit, because I want the tool to survive, the part to survive, the machine to survive, and hopefully the operator to survive. There's no need in a prototype environment to be that aggressive. If we get back in here making things, you're going to see a bunch of signs on the wall down by the computers that will give you a safer suggested speeds and feeds for the material that you're using. Okay? But for now, we'll take what we get here. Now that I have everything, well, not everything. When I called up a finish mill bore, this bore tab went bold. When I click that, it says bore diameter, and this says 0.201. Now, there's a significance to this number. It's not just the size we want. That's actually a tap drill for a quarter 20 thread. Every thread size has a corresponding tap drill size, and the result should give you 75% of thread. Okay? Because a tap is a rotary tool that we drive down through a pre-drilled hole to give us internal threads. Okay? And I don't know if you can see it from there, but there's a shiny edge that, on the front of this tap, that's actually considered a chamfer. Okay? Well, you don't get full thread until you get down to here. And if you don't get full thread through the hole, then you can't put the screw all the way through the hole. Okay? And we'll get to that a little bit later. Desired Z step. If I'm milling something very deep, a lot of times you don't do that all at once. You do it in increments. And this Z step is the size of that the Z travels down for each time it machines the geometry. Okay? So now with everything satisfied, I'm going to go in and I'm going to select all the locations that I want this to happen. And when those are selected, Gibbs gives us a really nice high-tech term to execute these processes called do it. So you see a dashed white line, which represents all the rapid traverse moves. And my actual machining path is this orange. Drive to Z depth in the center, feed out the radius, cut a circle. Okay?
And will it automatically adjust for whatever diameter end mill you're using?
Yes. When I select finish mill bore, it knows the end mill is on the inside because it's a bore, that stands for hole. And it's going to look at the circle diameter that I selected and do the math.
If you were to pick a diameter that's bigger than the hole you're trying to machine, would it stop you?
You mean a hole that's smaller than my end mill?
Yeah.
Yeah, it wouldn't create a path.
Okay, awesome.
Yeah, it's pretty good that way. Okay, tool number 2. And I'm going to select that wrongly titled roughing. And now when I go to the database, you see it's getting a little bit more aggressive. Again, my clearance points are the same, top of my workpiece, minus 15, go all the way through. And now I'm going to select a large circle and say do that. But I left something out. When we get down here, what that cycle that I just did, it went to the center, it drove to depth, and then it started cutting. In plastic, that's not a real big issue. In metals, that plunge is very harsh on the tool. Most of the time when our student workers break end mills, it's because they're trying to plunge. All right? That's the default. The next one is the same plunge, but now I can specify where that's going to happen. So let's just say I'm milling on the outside of something. I can have it plunge down off the part in midair, then come in and machine. Okay? The next two are when we're in the middle of the stock field and we have to get to depth. And those are ramp and helix. So what I'm going to talk about is ramp. Ramp is going to combine 2 or all 3 axes to create a gentle slope to get my tool from the top of the workpiece to the bottom of my cut. All right? Helix is going to do it similar, it's just going to do it in a helical circle. There are instances when that's more desirable than a ramp. Okay? So now I use the other high-tech term called redo, and now I see my sloping moves to get to the bottom. So now I'm going to call in my thread milling tool and a threading operation. Now, you see the feed rates on here are crazy compared to what they have been. And the reason is the machine programs in inches per minute. These feed rates are calculated based on inches per tooth on the tool. And if I go back to this tool definition, remember I said it describes a material that isn't there as a flute. Flutes and cutting edges, the amount is the same. So this has 6 cutting edges, where the end mill only had 2. So that's why that feed rate goes through the roof, because it makes the tooth load the same. All right? I've got a 1-inch finished cut diameter, and over here I see 16 TPI. We know what that is.
Threads per inch.
Threads per inch. Right underneath it, you see pitch. We know what that is. If I take this tap and I cut it lengthwise and I lay it down on the table, what I'm going to see is 60-degree triangles in succession. Okay? If I measure the crest of one triangle to the crest of the next, that's the pitch, that distance. Now the reason they give us both is because of the 2 different thread type designations. The US, which is outside diameter, and pitch, outside diameter and threads per inch, 1/4-20, or the metric designation is M6 by 1, 6 millimeter OD, 1 millimeter from crest to crest or pitch. By giving you both options, we can mix and match US and metric threads in the same workpiece at ease. Okay? Otherwise, we'd be doing 16.23795 threads per inch. Don't fact check me on that one. Okay, the material diameter, or essentially the tap drill for this 1" 16 is 950. I'm going to tell it to go inside a 3/4 inch diameter circle when it retracts, so it doesn't mill the edge of my thread when it comes out. And over here, I see the depth is -0.3. Now the reason I do that, similar to the chamfer on this tap, is the tool is set to this surface. I don't get full thread until this surface is all the way through my workpiece. That's what the extra depth is all about. So I can say do that, and you see now I have that helical thread path that is generated by the machine itself. I'm going to go back to holes, and now we get to talk about rigid tap. Same clearance heights, same top of my workpiece. That same extra depth to clear the chamfer on the tap. And that's my calculated RPM. And the feed rate is going to be based on the pitch of the thread, because the pitch from crest to crest is also the precise distance that thread travels in one 360-degree revolution. Following me? In order to hold a tap rigidly in that spindle, the machine has to match the RPM speed with the linear travel per revolution. Okay? So every revolution, it has to feed my 20 pitch thread 50 thousandths deep. Okay? And then we come to the bottom. So what happens in the bottom? It has to stop, right? Well, what did high school physics tell you about something in motion when it stops? Does it stop immediately? No. It ramps down, right? Well, it's beyond me how they do this, but they've figured out a way in this machine to match the rotational ramp down with the linear ramp down. Because if it doesn't match, the tap breaks. All right, so now we're stopped at the bottom of the hole. Now what has to happen? We've got to get the tap back out again. So we're going to spin it in the other direction at twice the RPM and twice the feed rate and match the ramp up to get it out. Like I said, I'm pretty simple, but to me, that's an electronic miracle. Again, and say do that. And my last operation is I have to cut this out of my blank. So I'm going to go back to tool number 2 and call up a contour. Again, now these speeds and feeds are getting very aggressive. Same clearance height, top of my workpiece. Back to that -15 thousandths in depth to cut all the way through. I'll auto plunge this time because it's going to be off the workpiece, because I'm going to add a feature over here called an entry and exit move. With that at 0, my tool comes over to start point, drives to depth, cuts around my piece, and retracts at that same start point. That's going to leave a blemish or a scar on the workpiece. What this does is it tells it to start out here, generate a 0.1 radius circle tangent to my geometry, come all the way around, and then exit off in a tangent circle. That makes that start and stop point invisible. Okay? And down here, the last thing I want to add to this is called a spring pass. Anytime we force a tool into a piece of material, I don't care what it is, we're going to get some resistance to the cutting. They refer to it as tool deflection. In the case of this plastic, I most suspect it's a material deflection, but the result is the same. It pushes away So therefore, our cut is going to be oversized. What this tells the machine to do is repeat that same path that you just took, but allowing things to relax back into position. It's going to make our piece more accurate and our repeatability part to part more consistent. Okay? So with everything said, now when I click on my geometry, I get a bunch of choices here. The first one is my cut direction. Textbooks call this up milling and down milling. There is not a machinist on the face of the earth that will refer to this as up milling or down milling. We call it climb milling and conventional milling. Now, I can't say 100%, but 99 point something ridiculous, we climb mill in the CNC machines because the forces are more consistent. We get a much better part-to-part repeatability, better surface finishes, albeit it does create more heat, okay? The reason we still have the option of conventional milling is this is going back into history before these when we had the manual machines, and we still have the problem in the manual machines. If you've ever put a nut on a bolt and pushed them back and forth without spinning, there's play there. It's called backlash. Well, in a climb milling, if you look down on top of the tool, it's trying to climb its way around the geometry. But what it's also trying to do is pull the stock. So if I'm driving my workpiece this way and my tool is trying to pull it, what it's going to do is it's going to keep jumping it into that backlash. Well, that breaks tools in a manual machine. So what we do is we change the feed direction to conventional so the forces are constant on the screw and there's no play. Now you can take climb milling chips in those manual machines, but they're very small, okay? Now, how did they eliminate backlash in these? It's a rather ingenious invention called the ball screw. The male portion of the ball screw is a hemispheric helical groove. The nut portion is a helical row of ball bearings that match the groove. But what it allows us to do is to pre-tension the ball bearings to virtually eliminate all of that end play between the nut and the screw. When I say eliminate it, we reduce it down to the 4th decimal place where we can tell the control to compensate for it. It actually is called out in the control as backlash compensation. So that's what allows us to do all of this high volume climb milling. The tool positions, basically tool left, tool right, tool on, inside, outside, and on. Outside, we're creating a male part. Inside, we're creating cavity. On is, say, if we want to engrave something, we want to be right on the geometry. We don't want to be offset. So I want the tool on the outside in the climb milling direction. I say do that. If I look at this upright, you see my tangent entry and exit arc. Now, that's all of the processes I require to make this part. And just about every CAM system out there now is going to have this next feature called cut part render, which is a fancy way of saying your part the movie. So I'm going to have it animate everything that I've done. Okay, now it looks fine. So I'm going to induce a problem. I'm going to go back to my first operation. I'm going to tell it big sin that my clearance point is now below the top of my workpiece. And you see the result in the animation. Okay? With 60 cents worth of plastic, not a real big deal. Now let me strap down a $3,000 casting with 25, 30 hours of machining already into it. This now becomes an epic. This now becomes the only thing coming between us and a pile of worthless rubble. So I can go back in here, seeing the problem, put it back where it belongs, redo. and now everything's fine. The other thing I want to point out to you is I have the first process that's highlighted in my list of processes over here, and they actually showed up in yellow when this part was being done. With 6 processes, it's not hard to find where the problem is. 25 to 30 processes. Now, any one of these that's highlighted is going to show up yellow in my cut part render. It makes it a lot easier to find where the problem is. But hopefully we will never have any problems. So my part's complete. The next thing I run it through is called a post-processor. What the system has got in this right-hand column now is a generic NC part program. What this post is going to do is it's going to convert it to machine specific. Now, these machines are similar, but they all have slight differences. So I'm going to tell it to do it for a Haas. I give it a program name. I click process. Everything I've done in the computer at this point is to get to here. All right? This is called G code. This is what the machine reads. It's not nearly as complex as it looks. There's 4 basic codes. You, depending on which axes you use them in, you can machine anything you can imagine. I'm going to start off with the first one, which is G0. G0 tells my machine from where you are to where I want you to wind up as fast as you can get there. It's a rapid traverse command. It's that 1,000 inches per minute. All right? The next one is G1. G1 tells my machine from where you are to where I want you to wind up at a specified rate. It's our linear cutting command. The first G1 in any program also has to have a corresponding F statement. How fast? All right. In this case, it's going to Z minus 15 at 2.29 inches a minute. Okay? The next 2 are opposites of each other. G2 and G3. G2, from where you are to where I want you to wind up in a clockwise arc. G3 is counterclockwise. All right? Each one of those is going to have a corresponding I or a J statement, which is going to refer to the incremental distance back to the rotation point of the arc. By varying the axes in which you use these, you can machine anything. So, in the spirit of a PBS cooking show, I've already put the program into my machine. All right, CNC vertical machine center, 20-station carousel. What can you tell me about the tools? Don't overthink it. Just looking at the tools, what can you tell me? I'm going to give you one. They're all different diameters. What else?
They do different things.
All different lengths. All right? Well, we have to deal with that. And where did it go?
Right from here,
Huh. I think I know who put it on there. Called the tool setter. What we're going to do is feed each one of these tools from Z home all the way up, down until it makes contact with my tool setter. It gives me this input. All right? Once it does that, it's going to store it in this register. This is called an offset. Again, the people who wrote this control call it a geometry offset. Just like Klein milling, not a machinist on the face of the earth calls it a geometry offset. Call it a TLO, because that stands for tool length offset. But we're simple and we need to know exactly what it means. Each one of these distances is how far off of Z home to get to here. All right. Now, when we're looking at this program, I said G's, but what else is there? I see Y minus 625, X minus 1.375. What are those?
Coordinates?
Kind of coordinates. Cartesian coordinates. Remember those things you graphed? Well, when you were graphing Cartesian coordinates, what did you start with?
An origin.
An origin. That's going to bring me back to these next sets of offsets called work offsets. Now, just like Z home is all the way up, XY home is over here. Now, this is telling me a distance off of home in X of 727 minus 6-point change to get to my defined center of the workpiece, which was established at Gibbs. Okay? One more number here is a Z reference, which is going to be the distance from the tool set location to my part reference. Okay? Now it knows where this part resides in my entire 16 by 30 envelope. Okay? Then the last thing I'm going to do is I'm going to add a high pressure stream of air. Because the biggest enemy of any cutting operation is heat. To combat the heated plastic, we use high pressure air. To combat it in metals, we flood it with a liquid. So, go get tool number 1. This is that finished mill bore. Go to depth, walk out the radius, cut a circle. Go get tool number 2. See the ramping move to get to the Z depth? And now the pocket concentric circles till it reaches the boundary. Now let's go get the thread milling tool. The pitch is generated by the G code. Enters a 3/4 diameter circle to retract. Here comes that electronic miracle. Again, if you don't match the linear and the rotational, you break the path. Go back to tool number 2. There comes the spring path, just repeating the same path that it just took. Exit circle. No. I can't pass this around because of the space age material called double-sided sticky tape. That was our work holding device for today. Now, anytime we cut materials with any kind of cutting tools, we're going to wind up with razor sharp edges that we have to deal with. This process is called deburring. This is a very basic tool called the swivel deburring tool. We do it in any kind of quantities. We're certainly not going to do it this way. The other manual deburring tools are files, there's abrasives. Normally I would throw this to the one who looked like he took the worst nap in my demo. If we were doing this in quantity, we might put it in a large drum with some small stones and soap and water and keep rolling it and let the stones crash into the edge and round them over. It was very common way back when. You put some glass in there and you make jewelry out of it. They also do the same process in a vibratory method in a large vat. They keep rolling it through the stones. Deburring can be very expensive, depending on how labor intensive it becomes. The most impressive deburring thing I ever saw was a Y tube that was made for the medical industry, and it had to be welded. Well, when you weld on the outside of the tube, what you create on the inside are microvoids. That is the end of the world to the medical industry, because those are tiny little incubators. So what they did is they hooked us up to a machine, and they forced an abrasively impregnated clay through this tube for 3 hours. And when they took it out, it was an absolute miracle on the inside of the tube. But it's about the most expensive deburring operation I've